all the electrostatics we deal with in this video are functions of Coulomb's law. So let's write Coulomb's law the way that you learned it. And that's the potential energy that's between two charges Q1 and Q2, separated by a distance r, is going to be a function of the magnitude of those two charges, the distance between them, and also a collection of constants, 4 pi epsilon naught, where epsilon naught is 8.85 times 10 to the negative 12 Coulomb squared per joule per meter. Epsilon naught is called the permittivity of free space, or also the vacuum permittivity. And that should give us a clue that this expression is actually only valid in a vacuum. In other words, when the charges are separated by a vacuum. If you have anything else between those two charges, we're going to have to somehow account for that. And we're going to account for that using the dielectric constant. So let's look at that on the next page. We are very often going to have our two charges separated by some sort of solvent. Whether it's a solvent or a solid material. And the modification to Coulomb's law is quite simple. The potential energy is equal to Q1 times Q2 over 4 pi epsilon naught times the dielectric constant times the distance between them. So this tells us that if we put in, say, hexane between those two charges, we saw that the dielectric constant of hexane is 2. The energy of interaction between those two things is actually reduced by a factor of 2. On the other hand, if we put in something like water, there's a dielectric constant of around 78. So that means that the energy of attraction between two unlike charges, or repulsion between like charges, is reduced by a factor of almost 80 when we dissolve things in water. And this is the primary reason why salts tend to be so soluble in water, because of its high dielectric constant. Discrete individual charges are just one example of what we call poles. So we can have a monopole, and that's just a positive or negative charge. We can also have a dipole, where something's neutral, but we have a separation of charge within the object. And of course, we're familiar with dipoles. We can also have a quadrupole, where we have something that is centrosymmetric, so it doesn't have a dipole moment, but we still have separation of charge. So a good example of a quadrupole, something with a quadrupole moment, would be carbon dioxide. The two oxygens are opposite one another and have a partial negative charge, and the center of the molecule has a positive charge. So there is some separation of charge, even though it's not, doesn't have a dipole moment. Now, when we look at these and look at the force law between them, or rather the potential energy law between them, we know for two monopoles, the potential energy is a function. If we have two dipoles at a particular orientation, so these dipoles are fixed in space, we'll explain how to deal with rotating dipoles later, we find that the potential energy equation has a r to the third distance dependent. So it's much shorter range than the one for unit charges, or for separated charges. If we look at quadrupole attraction law, or repulsion law, depending on the orientation, so imagine we have quadrupole here, and another quadrupole here. We can see that the closest interaction here is, so there would be some attraction here, but that's somewhat nullified by these others. We would find that this energy of interaction dies off as a function of r to the 7th. So it would be extremely short range. And that's why when we talk about intermolecular forces, we almost never really talk about ones caused by the quadrupole moment. We restrict ourselves to ion interactions and interactions between dipoles, or maybe interactions between ion and dipoles. So we don't really worry about higher order moments. So we don't worry about quadrupole moments, and certainly not octupole moments. Okay, so for the rest of the course, we're really only going to be worried about charges and dipoles.